All right, so good morning, everybody. What we are going to be doing today, we are going to go into chapter 4. There was the last section of chapter 3 that is covered this week too. Good morning. I am not having time to go over both. That was about related rates, and you just use the chain rule. You differentiate with respect to t. You make yourself a sketch of the problem. You find some equations, some relations that relate the given variables with each other, like the Pythagorean theorem or something of this form, or formulas for volume and for area, something like this. And then you differentiate with respect to t, plug in the values that are being given to you, the rates of change, and then solve for the unknown. That is it. So we do not have time to do more of those examples today, but what we will do is we are going to talk about the beginning of chapter 4. All right, so chapter 4 is, what is it that we're going to do with derivatives? Now the fun part of the class starts, basically. We have learned certain differentiation methods. Now we're going to see what it is that we actually can do with that. Also, one more note, there was an example on the video for the last section for 3.9. I don't know how it slipped in there, but because this is an early transcendental, we couldn't really, if you followed it, it's fine, but you couldn't really take the derivative of that function because it involved the derivative of tangent inverse function, which is a transcendental function. And we in this class right here have not talked about derivatives of trigonometric inverse functions. That is reserved for calculus 2. So if you looked at that video and you thought that, hey, what in the world is that? Well, you can look a little bit ahead in the book if you are curious. So the first thing that we're going to be doing today is we are going to talk about 4.1, maxima and minima of a certain function. So here's a definition that says that the absolute maximum or minimum is defined if the function f is defined on a set D containing a certain number, a certain value of c, then two possibilities. If f of c is greater than or equal to for every other output value on this set, then we say that f of c is an absolute maximum. If it is smaller than if the function value of c is smaller than any other value in this set D, then we say it is an absolute minimum, because you couldn't find any other value that gives you a smaller output value. Either one of those are being referred to as an absolute extreme value. Let's go ahead and have a quick look at some graphs. The first part of this class today is really definitions and theorems. And graphs help us to understand what these really say. So if I make such sloppy, really quick coordinate systems right here, I'm going to give us 4 different possibilities. The function is f of x is equal to x squared minus x squared minus 4. No, 4 minus x squared. 4 minus x squared. So in other words, if I am considering all of the domain, then this is the graph, and it continues, and that means right here, this output value is bigger than any other output value on this domain. And we say that there is a maximum, an absolute maximum. Is there an absolute minimum? No, there is no absolute minimum. All right, let's have a look at something else. What about something like this? This is the same function, but it's being restricted on just a certain part of its domain. In this case, we have an absolute max and we have an absolute min. Not brain teaser here. Now, there are two more options. This one, and then I could almost save me this one right here. So what about these two graphs? Well, in the first one right here, the third one from the left, is there an absolute minimum? Yes, there is. Is there an absolute maximum? No, there isn't. Because you can get closer and closer to this. You can always find one that will be closer to 4 if I am considering the same function here. So in this case, there is no absolute max. And then, of course, the last one is just reversed. Bless you. I hope you had your mask on. There is an absolute max, but there is no absolute min. Good? Not too hard to understand. Now, for a closed interval, I have to be a little bit more careful. For instance, my function, let's put some arrows on the x-axis. I could have something that looks like this. And will I be able to find an absolute maximum and an absolute minimum? Yeah. And as a matter of fact, the way that I drew it seems like right here, there's an absolute max. And down here, there's an absolute minimum. But what if I am drawing something like this? Is that an absolute minimum? Yes, there is. Where is it? It's located at this point, but the absolute minimum is this value. You need to get that straightened out. Where is it? At this x value. What is it? This output value. There is no output value that can get smaller. But this one right here does not have an absolute maximum. And why is this so? Because there is a discontinuity at this point. This graph is not continuous. So in order for us to guarantee that there is an absolute maximum and an absolute minimum on a certain closed interval, the function has to be continuous. That's good enough. If I'm telling you here's a continuous function on a closed interval, that means that you are guaranteed to find an absolute maximum and an absolute minimum. Both. Now, here's a good example, and I will come back to this one. Is there an absolute maximum and an absolute minimum? First of all, is this function continuous over this interval right here? Just shout out yes. Our audience won't mind if you are interrupting the class. So yes, this function is continuous. Is there an absolute maximum and absolute minimum? Yeah. Yes, there is. Absolute maximum seems to be located right here. Absolute minimum is right here, is this endpoint. There are some other interesting points though, and these are right here, and right there. These also see, oh no, it's good. That's what you get when you mess around. Yeah. So these points are not absolute, they are local. In other words, I am on a small interval around here. This value right here is going to be the smallest one. This is a local minimum. Right here, this is a local maximum, and this is a local minimum again, but it is not an absolute maximum because back down here, there's one value that is even smaller than this. So the moral of the story here is this, that I also have local maxima and minima. I have absolute and I have local minima. So suppose that C is an interior point of some interval I, for which f is defined. Now if f of c is greater than or equal to f of x for all x on this local interval, then f of c is a local maximum and respectively a local minimum if it is smaller than for all other f of x's on this certain given smaller interval, so to speak. Let me go and a moment. Now, here's the thing. If I'm going back to this graph from before, then I have how many local minima? 2. Right here and right there. Is there a local maxima? Yes, it is, right there. But here's the thing. These two kind of points are different. These two right here have something in common that this one does not. These 2 points have the following in common. And that means that if the derivative is defined and the value of c is in the domain of the original function, then if it has a local minimum, then the derivative is equal to 0 at that point. The local extreme value theorem. If f has a local maximum or minimum, then at a certain c, then f, and of course, like I mentioned earlier, the derivative is defined at this point, then f of the f prime of c is equal to 0. The derivative's value is 0. In other words, graphically speaking, there exists a horizontal tangent line. Note, this is what we call an if-then statement. In other words, it works in this direction. If there is a maximum or minimum locally, and the derivative exists at that point, then there will be a horizontal tangent line. This does not work in the opposite direction. if it would be working, then it would be what we call an if and only if. In other words, the converse is not true in this case. I can give you a quick picture that should convince you. So, for instance, a graph that looks like this, if I were to take the derivative of this graph, I would find two places where the derivative will be equal to 0. Does everybody see where those two spots would be? Where the derivative would have to be equal to 0, and that there are exactly two of them? Well, one is kind of obvious, that is right here. Here, the derivative has to be equal to 0. Why? Because there is a horizontal tangent line. But there is a second point right here where you also have a horizontal tangent line. So that means that the derivative is equal to 0 at that point. But that one right there is not a maximum nor a minimum locally. That one is. So in other words, I have to be careful. We will find out in the next section how to determine for what values of C that actually corresponds to either maximum or a minimum. Now, critical points, it has to be part of the domain of F. And there are two possibilities. A critical point is where your derivative is equal to 0, or the derivative fails to exist, but the function is defined at that given point. How does something like that look like? Well, just like what I have made a picture of earlier. Or I could even draw something like this. Now, if this is the graph of my original function f, then f is continuous. Let's make it a closed interval. On this closed interval, there is no discontinuity. There will be, if I would consider the derivative of this function, there will be 2 points where my function is going to be equal to 0, the derivative. And that happens right here, because there is a horizontal tangent line. But there is a third point, and that point is right here. And the derivative is not 0 at that point. The derivative does not exist. It is continuous over this whole interval, but it is not differentiable of this whole interval. Why? Because there is no horizontal tangent line. From this side, it approaches this. And from that side, the tangent line approaches a different value. So, not differentiable, it's a sharp corner. But it is a critical point. It is a local minimum. So what does that mean? I have to find the derivative. I set it equal to 0. Those are critical values. And where my derivative is not defined, but the original function is. Let's go ahead and first find some critical points of the following given function. So I'm looking at this function, and this looks to be like a rational function, because I have the quotient between two polynomial functions, x in the numerator and x squared plus 1 in the denominator. Could somebody elaborate on the domain of this function? Is there something bad going to happen at some point? We will remember from college algebra that if I have denominators, and we have seen it already earlier too, that the domain has restrictions for values that turn the denominator into 0. So the question is, is this happening here in this case? No. Why not? Because this denominator is never equal to 0. X squared plus 1, the solution to that would be plus or minus r, not a real number. Think about it this way. This would have to turn, x squared would have to be equal to -1 in order for this to be 0. This is not x squared minus 1. This is x squared plus 1. So in other words, this one right here is defined over the whole number line for all real numbers. So now I'm going to look at the derivative of this function. And to find the derivative, I'm going to use the quotient rule. Low d high minus high d low over low squared. So I'm starting low. Multiply this by the derivative of the top. Subtract the top function times the derivative of the bottom function. And divide this all by my denominator function squared. I'm going to simplify this. And what will I get? All right, let me do it in 2 steps. I'm going to have x squared plus 1 minus 2x squared over x squared plus 1 squared. And this will be, well, x squared minus 2x squared. I have 1 minus x squared divided by x squared plus 1 squared. Are there questions about this? Low, d high, minus high, d low. 2x squared, x squared, plus 1. Now I'm asking myself, when is this derivative equal to 0? This is easier than it looks. The only zeros that this function has are coming from the numerator. There are no zeros from the denominator because, for the same reason as the domain of the original function is all the real numbers, this one down here, the denominator, can never be equal to 0. So the only, and also f prime of x is defined for all x. Okay, now I have to use some math talk, which are element of the real numbers. This is just a shorter way to write for every x. This is an e, kind of a roundish e, and it means this x has to be an element of the real numbers. Everybody knows the symbol for the real numbers. Good. So when is it going to be equal to 0? Well, the derivative is going to be equal to 0 if 1 minus x squared is equal to 0. And this happens for plus or minus 1. Subtract 1 divided by -1 square root plus or minus of 1 is 1. Or just think about it in factored form. 1 minus x times 1 plus x. 1 minus x times 1 plus x is equal to 0. 1, -1. 2 values. 2 critical points. Good. We do not know whether these are corresponding to maxima or minima at this point. No idea. We already know examples. So let's go ahead and look at locating absolute extreme values on a closed interval. So if the function f is continuous on this closed interval, then I know there will be a local maximum and a local minimum by our theorem 4.2 from just a moment ago. The question is, how am I going to find those? So here's what you do. You find any critical points on the interior of that interval. Critical points, again, are either where my derivative is equal to 0 or f prime of that point is not defined, but it is defined on the original function. Well, it has to be because it is continuous. Then you just simply evaluate the function at these critical points, and in addition also at the end values, and then you just compare the values. So that's really it. Talking through this one more time real quick. You have a function, you're supposed to find the absolute extrema on a certain closed interval. What am I going to do? I take the derivative, I set the derivative equal to 0. I'm going to check whether or not these points are actually inside this closed interval. If they are, then I'm going to do certain things. I'm going to evaluate the function at those critical numbers, and I will evaluate the function at the end points. And then I just compare the output values. The smallest one was the minimum, the biggest one was the max. Idea clear? Let's do it. We have two examples here. We want to find the absolute maxima and minima of the following. For our first example, we are going to use f of x equal to x to the fourth minus 2x cubed. And the interval that we are interested in is the closed interval between -2 and 2. The second function is a little bit more interesting. The first function is just a polynomial function, which is rather boring. Polynomial functions are not very interesting. From a graphing point of view, we have some sort of an idea what they look like. With the second one, not exactly. So let's put this one on the bottom, and we will worry about that after this one, after A. So what is the first thing that I'm going to do? Find the derivative. Well, that's why I'm saying these are fairly boring, because the derivative part is boring. This is now the calculus part. This is 4x cubed minus 6x squared. And now I'm going to find my critical values by setting my derivative equal to 0, because the first part does not apply. This derivative is everywhere defined. There are no values for which this derivative is undefined. So setting this derivative equal to 0, I am just going to factor. What do we get? X minus 3. Did I do this right? Oops, 2x minus 3. Always check. 80% of the errors, if not even more, are being done while computing the algebra, not the calculus. I know that you know what 4 times 1 is and 3 times -2. All right, so can we do this really quickly without actually writing it down? One value is 0 coming from my first factor, and the second value from my factor here is going to be +3 divided by 2. Now, before I move on, I have to check. I only have to test those values now that are inside my interval of interest. Both values are in there. So that means I'm going to have to check now how many points altogether. I found out that my original function has something going on when x is equal to 0, when x is equal to 3/2. And what the original function has there are horizontal tangent lines. I do not know whether or not this is, first of all, even a local minimum or a local maximum. And I certainly do not know immediately that either one of those correspond to an absolute maximum or minimum. So what you have to do is just simply this. The interval, I need to push this a little bit further down. The interval was from -2 to 2. So I have to find out what is f of -2. I have to find out what is f of 0. I have to find out what is f of 3/2. And I have to find out what is f of -2. The biggest one will be the maximum, the smallest one will be the minimum. It's just that. So let's not waste too much time. F of -2 is equal to 32. F of 0 is equal to 0. F of 3/2, let me just give it away, is a -27 over 16. And f of +2, I have -2 here twice. F of +2 is 0. There's the whole question.
So, yes, please. You're putting it into the first equation, right?
In not equation, into the original function. So what does this mean? Understand the difference here. Where is the absolute max? At -2. What is the absolute max? 32. So it is located along the x-axis at -2, and the absolute maximum value actually is +32. If I would give you a quick rough sketch of this graph, it looks roughly like this. -2, +2, 3/2, 0. All right, this is a, oops, make sure that this is closed out. So the absolute maximum was at -2. There was a differential at 0, where the derivative was 0 at 0. There was a point at 3/2 where the derivative was 0. These are horizontal tangent lines. 3/2 corresponds to a local minimum, an absolute minimum. And +2, well, it's not quite as low as 3/2. Good. So let's do the same thing again with a function that is slightly more interesting. What's the point of making both of these? So I do not immediately know what the function of this looks like, because there is a 2/3 involved. It looks like as if there is some cubic root, and then we square it. Well, let's have a look. Closed interval between -1 and 2. This function is continuous between -1 and 2. First, I am going to find the derivative. Well, finding the derivative, if I have my function written like this, is a slight little bit tricky. There is an easier way to do this. I'm rewriting my function. I'm allowed to do this. In other words, I'm just multiplying this out. I'm getting 2x to the 2/3, x to the 2/3 times a negative x to the first. What do? I add my exponents. I'm getting x raised to the x to the 2/3 times x to the first is x to the 5/3. Algebra, ladies and gentlemen. So if I look at it like this, I can take my derivative slight little bit easier without having to use the product rule, in other words. I'm just using my power rule. 2/3 times 2, that will give me 4/3. Times x raised to the 2/3 minus 1 is a negative 1/3. Minus 5/3 times x raised to the 5/3 minus 1. Well, that's going to be 2/3 again. That part shouldn't have given you too much trouble. Now the problem is finding where this function is equal to 0. I have to rewrite it in order to see things. And what I'm going to do, I'm factoring. I am factoring out an x to the negative 1/3. Actually, a 1/3 times x to the, I can divide it by 3, of course. Let me just do it like this. X to the negative 1/3 over 3. If I take this out, what am I going to be left with on the inside? Well, in my first term, that's not a brain teaser. What is left in here if I take x to the negative 1/3 and 1/3 out? Oops. 4. And what am I left in here? Well, a negative 5 is clear. And x to the what power? Think about it backwards. If you have to multiply it back out, it needs to give you x to the 2/3. So at that moment you add. But if you take it out, you subtract, because you divide this term right here by x to the negative 1/3. It's just going to be x to the first. X raised to the 3/3. 2/3 minus a negative 1/3 will give you 1. And look, if you now multiply this back out, you would get this again. The good part comes now if I'm rewriting this as 4 minus 5x divided by 3 times x to the 1/3 or the cubic root of x. That doesn't matter right now. This was the tricky part. Now the part is to identify critical points. Again, do I need to stop right here for a second? I don't know how much more time we have. Well, we have 10 minutes. Do I need to stop right here to explain how we got from here to there? Please let me know if I have to do this again. No problem. We have a minute to do that. Most of you are not familiar about that I can also factor out fractional exponents and even negative rational exponents. Let me just do it like this, and then I'll give you some time at home to think about it. If you do the old school factoring, oh, wow, like the one that we did up here. Hold on, let's actually use that. Where was it? There it was. This one right here. Let me move this slowly down. because this is the exact same strategy. What do I do in order to factor this? Well, I locate common factors out of my numbers. Well, that's easy. Greatest common factor here is, well, there is a 2 in there, and then you take the x with the smallest exponent. And in this case, 2 is smaller than 3. Hey, that was a 4, wasn't it? No, it was a 3. So 2 is smaller than 3. So the greatest common factor is 2x squared. And what I do with this now, whoops, I'm throwing away my marker here. I am multiplying this by 2x squared, and I divide it by 2x squared at the same time. Because this doesn't change anything. What I have to do now, I need to make sure that this polynomial, this second factor, is going to be evenly divided by 2x squared. Still haven't changed anything. This is nice because both of these monomials are evenly divisible by 2x squared. What do I do now with these two exponents? Top minus bottom. You divide, you subtract the exponent. You multiply, you add the exponent. So in other words, I end up with 2x minus 3. Good. Now let's do the same thing with the more complicated one. There it is. I'm picking 4/3. Actually, let me write it like this. 4 times x to the negative 1/3 over 3 minus 5 times x to the positive 2/3 over 3. And look, what do they have in common? What is the greatest common factor? A 1/3 shows up. And an x, well, what's the smallest exponent that you see? What's the smaller one? A negative 1/3. So in other words, I'm going to take this, and I will take 1/3 x to the negative 1/3 out, and I will divide everything by 1/3 times x to the negative 1/3. I wish I would have not focused on the 1/3 part, but it's just multiplication with the reciprocal, so the 3's are canceling out. The exponents that most people are being thrown off with. So 4/3 divided by 1/3 is just 4. But what about the exponents right here? X to the negative 1/3 divided by x to the negative 1/3 is minus a negative 1/3 is plus 1/3, which is 0. X to the 0 is just, oops. So no, let's actually write it down. 1/3, negative 1/3, minus a negative 1/3, minus 5, and here's where the meat is, 2/3, minus a negative 1/3. This is 0. That means I am left with 4. Here I'm getting 2/3 minus a negative 1/3 is 2/3 plus 1/3, which is just 1. Ta-da-da-da. Factoring. Factoring will make easy with Kozlowski. I bet you probably have never seen it this way that I just did it, but that's what's going on in the background. Multiply back out. So back to our question. Is my derivative undefined at any given points? Yeah, it is. When is this denominator equal to 0? You got it when x is equal to 0. Don't leave me hanging here like this. The cubic root of 0 is 0. 3 times 0 is 0. So in other words, the denominator part would be 0 when x is equal to 0. That means that this function is not defined. F prime of 0, or in other words, it does not exist. That makes 0 a critical value. The other one comes from your numerator, 4 minus 5x. It's just as easy as we did it the first time around. Subtract 4, divide by negative 5, 4/5. Oops, my 4s are not getting better. So that means now I have to test how many values? 4. I cannot forget about the undefined, where my derivative is undefined. So I have to, what was the interval actually? -1 to 2. I have to find now, that was the first part, finding the critical values. Now I'm going to find f of -1. I'm going to find f of 0. I'm going to find f of 4/5, and I'm going to find f of 1. You may use your calculator for the third one here. Let me just cheat real quick. Actually, for the first one, -1, that is easy to just do in your head. 2 minus a -1, that is 3. -1, take the cubic root out of it, is -1. -1 squared is +1. That is going to be equal to +3. Was that too fast? Now f of 0 is just as easy. What is f of 0? 0. That one right there, I said that's the one that I'm even going to look at real quick. That would be approximately 1.03. We could do it more accurately with the fractions, but with the radical signs, but it doesn't matter. And g of 2 again is 0 as well. Hey, why do I have 1? 2 was the end point. And of course, this is 0 because that's where the second factor of your function is 0. F of 0 is 0 because the first factor is 0. F of 2 is 0 because your second factor is 0. F of -1 was 3. And f of 4/5 is. So what does this mean? How many? So an absolute maximum is at. Oops. There is your absolute max. How many absolute minima we have?
1. Absolute.
Absolute minimum.
Oh, 2. Sorry.
We have 2. That's what I was about to say. At least if your eyesight says something different, I see 2 values that spit out 0. So we have 2 absolute minimum. That the word absolute does not mean there is allowed to be only 1. It only says that it doesn't get any smaller anywhere. So I'm going to have 2. Good? All right. This was a productive. Hold on. How do I now go in here and stop recording? There we go.